Here is the ninth behavioral design pattern from the famous Gang of Four design patterns book. This one is called strategy pattern, and it is a pattern you use when you want to define a family of algorithms, encapsulate them, and make them interchangeable. I'll start with a quick summary of what we are trying to accomplish with this pattern. The strategy pattern is a good choice when you are trying to accomplish the following. You have a family of algorithms that you want to make interchangeable. You want to vary the algorithms independently from the clients that use it. Okay, let's go through the points one by one. The key to this pattern is that you have a family of algorithms that you wish to use in your application architecture. Each algorithm has a common interface but a unique implementation. You want an elegant solution for making the algorithms interchangeable. The strategy pattern does exactly that. It defines an abstract strategy base class that implements a common interface for the algorithm. Each derived concrete strategy class inherits the interface and implements it in a unique way. A client can declare a variable of type strategy and initialize it with a specific concrete strategy class to use that specific algorithm. Changing algorithms is as simple as assigning a different concrete strategy to the variable. Because all strategy classes share the same interface, everything keeps working. The benefits of the strategy pattern is that it completely shields clients from the implementation of an algorithm. When you change an existing algorithm or add a new one, the client code will keep working and does not need to be refactored. This loosens the coupling between the context and the strategy classes, and that is a good thing. Okay, here is the UML diagram of the strategy pattern. The heart of the pattern is the strategy class. This abstract base class declares the public interface of the interchangeable algorithm. The diagram shows one single interface method called algorithm interface. There are three derived strategy classes called concrete strategy A, concrete strategy B, and concrete strategy C. Each concrete class implements the algorithm interface method in a different way. And finally, there is a context class. This class performs some kind of operation for which it needs the interchangeable algorithm. The class has its own public interface, shown in the diagram as a single context interface method. The implementation of this method uses a concrete strategy to perform the operation. Here's how that works. The method contains a field of type strategy and initializes it with whatever concrete strategy it needs to perform the operation. Every time the context class needs to use the algorithm, it uses the variable to call the algorithm interface method. The context class has no knowledge about the implementation of the algorithm, as it only ever uses the strategy base class. To demonstrate the pattern, I will show you a common IT problem. Let's say I have a database of people with everybody's name split into a first name and a last name field. I also have an external data file with names that I need to match against my database. Now, here's the problem. The names are spelled differently in the data file. First names are abbreviated. The names contain extra spaces. The capitalization is all wrong, or part of the name is missing. I need to write a compare algorithm that matches the names in the data file with the names in my database. I am going to write 3 algorithms and use the strategy pattern to run the match 3 times for each algorithm. So, I will implement the pattern with the following classes. Let's take a look at the code. I will start with the nameComparer class. You can see that it's an abstract base class that declares a single compare method. The method receives 1 imported name as a string and 1 name record from the database as a struct. The method should compare the 2 names, return true if they match, or return false if they do not. And here is the exact comparer class. It simply joins the first name and the last name together with a space, and then matches this full name against the imported name using an exact string compare. The method returns true for an exact match and false if the names do not match. So you can imagine that this comparer is going to miss a lot of names. Any imported names with extra spaces or abbreviations or strange capitalizations are going to be missed. So here is an improved algorithm. The fuzzy comparer uses regular expressions to strip all non-word characters from the imported name. It then splits the name into a first name and a last name, and compares everything in lowercase. This is a much better algorithm, but it still cannot process abbreviations. So here is the third algorithm. The abbreviation comparer inherits from the fuzzy comparer and also matches abbreviated first names. So M. Smith will now match Mary Smith. And here is the name importer class. You can see that it has a constructor for setting up a name comparer strategy. There is also a match method here that compares a given name database against a list of names to import. The method uses the current name comparer strategy to compare each name and displays each match on the console. Okay, and finally, here is the main program method. You can see that it initializes a database of 10 names and another list of 10 names to import. It then uses all 3 name comparer strategies to match the imported names against the database. Let me run the program to prove that everything is working. I'm compiling the code now. And now I am running the program. And there you go. The exact comparer strategy only finds a single name, Iris West. The fuzzy match does a lot better and is able to match a total of 7 names. But the abbreviation name comparer outperforms everything and is able to match all 10 names in the import list. Thanks to the strategy pattern, you can easily swap these name compare algorithms in and out to find the best solution for any import list. Okay, here is a quick checklist that you can use to implement the strategy pattern. First, identify a family of related algorithms. Then create an abstract strategy class that defines the algorithm interface. Implement the algorithm interface in one or more derived concrete strategy classes. And finally, create a context class that dynamically creates and loads the correct algorithm. And here are some final comments. The strategy pattern is very similar to the template method pattern, but the difference is granularity. The template method pattern differs substeps of an algorithm to subclasses, while the strategy pattern differs the implementation of the entire algorithm to subclasses. There's also a lot of similarity between the state and the strategy patterns, but the difference here is intent. The state pattern uses subclasses to change the behavior of methods for different internal object states, whereas the strategy pattern uses subclasses to replace the implementation of an entire algorithm. And finally, you often see the strategy pattern combined with the flyweight pattern. This combo pattern lets you support several types of flyweight objects that differ in their implementation. Okay, so here is a summary of everything we have learned in this lecture. The strategy pattern defines a family of algorithms, encapsulates them, and makes them interchangeable. The pattern completely shields clients from the implementation details of an algorithm. The strategy pattern is very similar to the template method pattern, but differs in granularity. The pattern is also similar to the state pattern, but differs in intent. The strategy pattern is often combined with the flyweight pattern to support several types of flyweights.